Hello, this is the Test 1 review. The purpose of these test reviews is to highlight the most important topics that will be on the test. As mentioned in the syllabus, test problems fall into two general categories. There are calculations and then concept questions that are in the form of multiple choice questions. Calculation questions will be very similar to the review problems that are posted along with the Course Compass homework. Now remember, those problems will not affect your final grade. They are strictly for your review. You can choose to do them or not. The best way to study for the test is to look over these review slides and do those review problems. Also mentioned in the syllabus is that you can use whatever handwritten notes you want for the test. You cannot look back at the slides or the lessons when you do the test. So for this test you would need your calculator as well as table A6, which you should already have printed. So first topic is a definition. Data or observations that have been collected. Note again that it does not say here that data are numbers. Data can be numbers, but they don't have to be numbers. They can be lists of words. The word data is plural and the word datum is singular. Data falls into two general categories, quantitative and qualitative. Quantitative data is in the form of numbers. Qualitative data is not in the form of numbers. Quantitative data is further broken down into two categories, discrete and continuous. Discrete data has to be of a certain type, like integers. Continuous data, they don't have to be of a certain type. They can take on any value within some range. A couple of important definitions here. A population is the complete collection of all elements to be studied. Population is not necessarily a group of people. It can be, but it's just a generic term for everything that we're interested in a particular scenario. A parameter is a numerical measurement obtained from surveying every single member of the population. So if we get information from every single member of the population and we calculate something like a mean or a proportion, that number would be considered a parameter. Now a sample is a subcollection of members from a population. It's not the entire population. It's maybe only a few members or maybe several thousand members, but it's not the entire population. A statistic is a numerical measurement obtained from surveying every single member of a sample. Now, the difference between a population and a sample and a parameter and a statistic is what the field of statistics is really all about. I really want to know something about my population. In other words, I want to know a population parameter. But that's very difficult, if not impossible, to do because it requires me to survey every single member of the population. So instead I look at a sample, which is just a few members of the population. I get information from those few members and calculate a statistic. That statistic is an estimate of the population parameter that I really want to know. The main point of Chapter 1 is about choosing a sample. Choosing a sample is the first step in doing some sort of statistical analysis. It's also the most difficult step to some extent. As we pointed out, if sample data are not collected in an appropriate way, the data may be so completely useless that no amount of statistical torture can salvage them. If you don't collect your data appropriately, you can't crunch the numbers enough to get a valid result. Our first type of graph we talked about was a histogram. Idea behind a histogram is to get a picture of what the data looks like. So we start off by constructing a frequency histogram, or frequency distribution, which is showed here on the left. So the idea there is that we divide the range of data values down into several different subintervals or classes or bins, and then we count the number of data values that are in each one of those classes or bins. That's the frequency. And so that summarizes the data, but it's still a lot of numbers. We don't like to look at numbers, we want a picture. So our picture is called a histogram, shown there on the right. So there we have one column for each class, and the height of the column equals the frequency. A normal distribution is a very special type of distribution. Here we see this distribution of the weights of men. in the frequencies, we see they start at a low, they increase to a max, and they decrease to a low again. And we have roughly the same number of classes below the max as we do above. Any set of data that has a distribution that fits this pattern is said to have a normal distribution. A histogram of that distribution will look like this. Notice that it starts at a low on the left, increases to a max in the middle, and then decreases to a low again on the right. We said that shape has a bell curve shape. A bell curve and normal distribution are almost used synonymously. Our first measure of center we talked about was a mean. A sample mean is denoted by x bar, and it's simply calculated by adding up all the values in the sample and divide by the number in the sample. The median, that's where we line up our data values from smallest to largest. Pick the one right in the middle. That's denoted x bar. The mode is the value that occurs most frequently. Measures of variation are measures of how spread out the data is. Standard deviation is a little complicated to calculate, but it's also very important and very meaningful. The standard deviation, a sample standard deviation, is noted by S. Here's the formula. Now we're not going to calculate standard deviations by hand on the test. Instead, we're going to use our calculator. The variance is another measure of variation. It's noted by S squared, and it's simply the square of the standard deviation. Now we can calculate standard deviations on our calculator by first entering the data into a list, which we've done several times before, and then we select the option Stat, Calc, and then option 1 for one variable statistics. Using standard deviation, we got what we call the range rule of thumb, which said that 95% or a quote-unquote vast majority of all our values lie within 2 standard deviations of the mean. One use of standard deviation is we use it as almost a unit of measurement. We measure how far a data value is from the mean in terms of standard deviations. So a usual minimum value is the mean minus 2 times the standard deviation, and then a usual maximum value is the mean plus 2 times the standard deviation. Any number that's between that min and max value would be considered usual or ordinary. Anything outside of that range would be considered unusual. Doesn't mean that something's wrong with it, just that it's unusual in the context of that set of data. Similar to the range rule of thumb, we have this empirical rule, which applies to data with a normal distribution. If we look at the range of values x bar minus s up to x bar plus s, where x bar is the sample mean and s is the sample standard deviation, we get a range of data values. Our rule says that 68% of our data values are within that range. Or we say that 68% are within 1 standard deviation of the mean. If we look at the range from x bar minus 2 times s up to x bar plus 2 times s, we get a wider range of values. Those values we say are within 2 standard deviations of the mean. The rule says that 95% of our values are within 2 standard deviations of the mean. And then lastly, it says that 99.7% of our values are within 3 standard deviations of the mean. Okay, when we calculate means, we have 2 different types of means: sample means and population means. A sample mean is denoted x bar, so we add up all the values in a sample and divide by the number in the sample. That is a statistic because it's calculated using information from a sample. If we have values from every single member of the population, we add them up and then divide by capital N the number of values in the population. We get a population mean, which is denoted by the Greek letter mu. That is a parameter because it is calculated based off information from every single member of the population. Likewise, when we calculate standard deviations, we have a sample standard deviation, a population standard deviation. Sample standard deviation is denoted by S. It's the formula there. And then we have population standard deviation, which is noted by sigma. And again, the difference is that S is calculated using information from a sample, and sigma is calculated using information from every single member of the population. S is a statistic, and sigma is a parameter. Okay. In Chapter 3, we also saw this idea of a z-score. A z-score of a given value is the number of standard deviations it is from the mean. And here's the formula, x minus x bar divided by s. This is a formula that we'll be using quite frequently starting in chapter 7. So you'll want to write this formula down on your notes. Using z-scores, we can restate our range rule of thumb, which originally said that ordinary values are within 2 standard deviations of the mean. In terms of z-scores, that means there are z-scores between -2 and +2. Percentiles, we're not going to be calculating percentiles on a test. We just want to understand what they mean. So as example we gave in the first lesson it was about my son Martin. His weight at 12 months was 25 pounds. The doctor said he was at the 90th percentile, or state another way that 25 pounds is the 90th percentile, and that means that Martin is heavier than about 90% of kids his age. That's what a 90th percentile means. It's a data value that is greater than 90% of the other data values. 50th percentile is a data value that is greater than 50% of the other values, so on and so forth. Associated with percentiles, we have box plots. A box plot is a graphical description of the 5-number summary. Remember, 5-number summary consists of the first quartile, which is the 25th percentile. It also starts with the minimum, the first quartile, the second quartile, which is the 50th percentile, which is the same as the median, and then we have the third quartile, which is the 75th percentile, and then we have the maximum value. Here are 2 box plots that compare 2 different sets of data. This is not one that we looked at in earlier lesson. This is a completely new box plot. But here we're comparing the ages of the people who won the Best Actress Award to the people who won the Best Actor Award. And we can compare those two. We see that, for instance, the best actress, the ages of the best actress is a little more spread out than the age of the best actor. We see that the median for the best actress is quite a bit smaller than the median for the best actor. And so that's again, a box plot is a graphical description of the 5-number summary. It also allows us to compare sets of data. In chapter 10 we talked about correlation. Correlation is just a fancy name for relationship. So we start off having a scatter plot of this variable weight and miles per gallon of a car, and we saw that those dots, as we move from left to right, the dots move down. That means that as weight increases, miles per gallon decrease. So we say that those 2 variables, weight and miles per gallon, have a negative linear correlation. Again, correlation is a fancy name for relationship. Linear means that those dots almost form a straight line, and negative means that that line slopes down from left to right. When we see graphically that we have a linear relationship, we want to measure the strength of it. We do that with this quantity called R, which is named the linear correlation coefficient, or also called the Pearson correlation coefficient. It takes on values between -1 and +1. The closer it is to -1 or +1, the stronger the linear relationship. It's close to 0, that means that there's no linear relationship. R values can be calculated very easily. First you have to enter your X values into one list, your Y values into another list, and you choose this option, your stat test, and then F, linear regression t-test. Remember, on some calculators it may be option E. You choose beta and rho not equal to 0, and scroll down to the bottom and it will give you the R value. So then if we see that in our sample we have a linear relationship, meaning if R is close to -1 or +1, we then want to determine if in our population we have a linear relationship between those 2 variables. And we can do that using this table A6. Little n is our sample size. Alpha is called the significance level. It's a measure of how confident we want to be in our answer. And so typically we use 0.05 for the value of alpha. So if we go to that column and down to n equals 7, in this case dealing with the cars because we had 7 cars, our critical value is 0.754. If the absolute value of R is greater than the critical value, then we conclude that there is a linear correlation in the population. If the absolute value of R is less than the critical value, then we conclude that there is not a linear correlation in the population. So in the example we did in class, the absolute value of R is 0.944, which is definitely greater than the critical value. So we conclude that there is a linear correlation between weight and miles per gallon in the population of all cars. So if we conclude that there is a linear relationship between two variables, we can next calculate our regression equation. And the idea behind a regression equation is we want to fit a straight line to that data. We want a straight line that captures the trend of that data. We did that on our calculator using that same command F linear regression t-test that gives us the slope and the y-intercept of our regression equation. Here is the regression equation for the weight in miles per gallon example. And so here's what we can do with it. Suppose that a car weighs 3,000 pounds. We can plug in 3,000 for the weight, do the arithmetic, and get a predicted miles per gallon for it.